Hey everybody, Matt from 90th percentile.ca here. For access to more study notes, practice questions, mock exams, and end of chapter question videos, visit 90th percentile.ca and sign up for your free trial today. Link below in the description. This learning module is common probability distributions. Key two topics in this module are discussing how discrete and continuous variables have slightly different probability distribution functions and cumulative distribution functions. To put it really simply, a probability distribution function just states the probability of x being equal to a certain value. You could say, the probability of x being equal to 2 is, let's say, 50%. So that's described in a PDF or probability distribution function. And the continuation of that is the cumulative distribution function, which just takes the cumulative probabilities of all the values of the variable as of a certain range. So it just sums up everything in the PDF. Moving on, once again, most important stuff on exam days in the second half, where we're talking about the different types of distributions. So as of right now, we've only talked about the z distribution, but we're also going to be introduced to the t distribution, the chi-square distribution, and the f distribution. These two are very closely related. The t distribution is essentially the same thing as a z distribution, but it's typically used when the sample size is small, so n is less than 30, and it's assumed that we don't know the variance of the population. Very similar, you'll see that the graphs have similar shapes as well, but we'll get into it in a little bit more detail later. These two, the z and the t, are, in my opinion, most likely to show up on exam day, so we got to make sure that we know the assumptions underlying each, we know when to use them, we know what the graphs and the distributions look like, etc. But going forward, we also have the chi-square distribution and f distribution. We need to know all the same things as the z and the t. These are a little bit less common and they model some different things. But once again, we'll get familiar with the shape of the graph and the underlying assumptions in the models. So with that, let's get into the questions. X is a discrete random variable with possible outcomes 1, 2, 3, and 4. Three functions, f of x, g of x, and h of x, are proposed to describe the probabilities of the outcomes in x. So we have the x values, or the values that x could take here. We have the probability of each in these three different probability functions. The conditions for a probability function are satisfied by, and basically, so a probability function of a discrete variable, I actually drew a quick diagram here of this function. So you can see you have the x values, the values that x can take on the x-axis, and the probability of each on the y-axis. So for if x is 1, or there's a 20% probability that x is 1, 25% that it's 2, as you can see right here, 25%, 50% that it's 3, and 5% that it's 4. So for a probability function to make sense, all of these values have to add up to 100%. That's a key thing that we're looking for here, and that's what the question's asking. If the values that x can take are only 1, 2, 3, and 4, it doesn't make sense that these probabilities would not sum up to 1 or 100%. So g of x is going to be our answer. Like if you were to add these up, it doesn't add up to 100. Add these up, it doesn't add up to 100 either. So g of x is our answer. And I just wanted to show the visual here. This is for a discrete random variable versus what we've seen for continuous random variables will just look something like this, where we have the continuous line. But here we have the discrete values because the discrete values can only be integers. So same kind of concept, just the presentation is a little bit different. The value of a cumulative distribution function, f of x, where x is a particular outcome for a discrete uniform distribution, sums to 1, lies between 0 and 1, or decreases as x increases. So I kept this example here from the previous question, the probability function. The only difference between probability function and the cumulative distribution function is that the cumulative is just going to sum up all the probabilities as the values increase. So if I was to draw this really quickly, f of x in the light blue, the graph would look something like this. The first value is just going to be the same for the cumulative distribution, so 0.2. And then here, for 2, it's going to be 0.45, which is 0.2 plus 0.25. So it looks something like this. And then for when x is 3 in the cumulative distribution function, it's going to be 0.5, so the probability of 3 plus the probability of everything before. So we come all the way up to 0.95 here. And then on the last value, 4, probability of that is 0.05. So that brings us all the way up to 100%. So the cumulative distribution function at the latest value will be at 100%. So 1.00. And if, coming back to the question, if the value of the cumulative distribution function f of x, where x is a particular outcome, then if x is any one of these values, the answer must lie between 0 and 1. The cumulative distribution function for a discrete random variable is shown in the following table. So it's a cumulative distribution function. And we have values of x going from 1 to 6, and then the cumulative probability. The probability that x will take on a value of either 2 or 4 is closest to, so we need probability of x equal 2 plus probability x equals 4. So we can come to the graph here. Important to note that this is a cumulative distribution function, not the individual probability of, if we're looking here, x is 2, the probability of x being equal to 2 is not 0.25, it's actually the difference between these two, because the probability of x being 1 is 0.15, and then the probability of x being 2 or 1 is 0.25, so 2 must be the difference, which is 0.1, and then for 4, it's the same thing, it's the difference between the 0.5 and the 0.6, which is also 0.1. Sum these two together, and we get 0.2, which is our answer. A random number between 0 and 1 is generated according to a continuous uniform distribution. What is the probability that the first number generated will have a value of exactly 0.3? I kind of touched on this in one of the earlier modules, but if you forget the 0 and 1 for now, and let's just have two variables. One can be 0 to 10, and this is discrete. And then we'll have the same one from 0 to 10, that's continuous. In the discrete distribution from 0 to 10, the value can either be 1, 2, 3, 4, all the way to 9 and 10, just the integers. So the probability of the value being equal to one of these would be 0.1 or 10%. In a continuous distribution from 0 to 10, it's kind of a weird stats concept, but there's effectively assumed to be infinite possibilities between 0 and 10, because the value could be like 2.2, 4, 5, 6, and the decimals could just go on forever, all the way to infinity. And due to that, the probability of it being exactly one value, so in this case 0.3, is 0, because there's 0% chance of it being exactly this value. But when you take the cumulative probability of it being equal to 0 to 10, it's 100%. So the answer would be A. For a binomial random variable with 5 trials and a probability of success on each trial of 0.5, the distribution will be skewed, uniform, or symmetric. So a binomial random variable is one that can take only two values, either 0 or 1, or a fail or a success. So if there's 5 trials here and the probability of success on each trial is 0.5, if you were to draw the graph again of the probability function, this would be fail, this is success. Both of them are going to have a probability. Color that in. Both of them are going to have a probability of 0.5. So the distribution is symmetric because this is identical to this. A portfolio manager annually outperforms her benchmark 60% of the time. Assuming independent annual trials, what is the probability that she will outperform her benchmark 4 or more times over the next 5 years? So here, the first thing you have to do is recognize that this is a Bernoulli distribution, which simply put is just a simulated number of tests where the variable that you're distributing is either a fail or zero or a success, which is one. So in order to calculate the probability of four or more times that she outperforms her benchmark, we have to look at the formula to calculate the probability of a trial or of an outcome in a Bernoulli distribution. And that is, it's kind of similar to what we touched on earlier with the multinomial distribution and the combination and permutation formulas, but formula is a little bit different where this would look familiar to us. So we have n, which is a sample size, x is the number of successes or what we're choosing, and then x here again, factorial, and then we have to multiply this by the probability of x. So in this case, the probability of x is the probability that she outperforms the benchmark. And we also multiply that by 1 minus the probability and put this to the power of n minus x. So if we were to do this to calculate the probability that she outperforms 4 times, it would look like this. N is 5 because it's 5 years. And then 5 minus 4 factorial, we're choosing 4 successes, times 4 factorial times the probability, which is 0.6. And then multiply by 1 minus probability, so 0.4 to the power of 5 minus 4. So if you were to run this calc out, we get a probability of 0.2592, which is an answer in A, but they're trying to trick you once again, because this is the probability of 4 successes, not 4 or more. So if we wanted to do 4 or more, we also have to calculate the probability of 5 successes, which would be the same thing, but here, instead of 4, we're using 5. Multiply it by 0.6 times 0.4 to the power of 5 minus 5, which is 1. And if we ran this out, we would get 0.0778. And you sum these two together, because this is the probability of 4 times that she outperforms, and this is the probability of 5. So to get 4 or more, you have to sum the two together, and we end up getting somewhere around 0.34, which is B. Which of the following events can be represented as a Bernoulli trial? So what I just spoke on earlier, a Bernoulli trial is a simulation which there's only 2 possible events, a 0 or a 1, or a fail and a success. So let's look through our options here. Flipping of a coin can either be heads or tails, so that's going to be our answer. But if we wanted to continue down the list, the closing price of a stock, I believe would technically be a continuous distribution, because I mean, let's say the stock price like 99.99. I guess there might only be 2 decimals effective depending on like what trading platform you're using, but in principle, the closing price could be whatever. There could be a bunch of decimals here where you're paying like fractions of a penny. So this is actually continuous. And then the picking of a random integer between 1 and 10 is a discrete distribution with integer values being 1, 2, 3, 4, 5, all the way to 10. And there's more than 2 results, so that is not the answer either. A stock is priced at $100 and follows a 1-period binomial process, so only 2 outcomes, with an up move that equals 1.05, so 5% increase, so the stock price would be 105, and a down move that equals 0.97, so the stock price would be $97. If 1 million Bernoulli trials are conducted and the average terminal stock price is 102, the probability of an up move P is closest to which one of these? Here, the 1 million trials, I mean, the way they included this in the question, it's okay. It's not really relevant for how we're gonna solve it, because, like I said, it's a 1-period binomial process where the stock price can either be 105, so it starts at 100, and it can be 105 or 97. And we need to calculate the probability of the stock price moving up to this, and then the inverse of that would be 1 minus the probability of the up move up here. So if we were to put this into simple algebra, it would basically look like this. So 105 is 105 times the probability plus 97 times 1 minus the probability of an up move. Put PU there, equals 102. So 102 is the effectively the expected value. So if we were to run this out, just kind of, simple algebra, 105p plus 97 minus 97p equals 102. We can bring all this stuff over here. So it would be 8p, if we're isolating for the p's here, 105, 97 minus 97 is 8p, and then 102 minus 97 is 5, so p would be 5 over 8, which is 0.625. It's the probability of an up move, and then the probability of the down move would be 1 minus that, but we're not worried about that. So the probability of the up move is 0.625. State the approximate probability that a normal random variable will fall within the following intervals. We have the mean plus or minus 1 standard deviation, plus or minus 2, plus or minus 3. I took an image off the internet here just because I thought I would draw it a little bit better. So we can see a typical normal distribution, and an assumption with the normal distribution is that given these outcomes that follow this curve, if you take the mean and then add 1 standard deviation, this example uses 50 as a mean standard deviation of 10, 68% of the values would lie between plus or minus 1. So here's 68%. For B, same thing, but now we're dealing with 2 standard deviations, which is 95% of values will be contained within that. And then finally, the last one is mean plus or minus 3 standard deviations, which is around 99% of values will be included in that. And if you wanted to go out all the way here, technically these values would go on forever and it could, go to infinity, but the likelihood that this distribution with the mean of 10 and standard deviation of 10 would be equal to something like 25,000 it's not 0, but it's extremely unlikely. So that's why we assume that, most of the values are contained within 3, 2, or 1 standard deviations. The total number of parameters that fully characterizes a multivariate, so multivariable, normal distribution for the returns of 2 stocks is what? So what is a parameter? First, the parameters of a normal distribution are the mean, the mu, the mean, and the variance. So for if we know a variable is normally distributed, the only 2 data points we need are the mean and the variance. And from this data, we could create the normal distribution, and we can calculate the probability that x is maybe less than or equal to a value, or greater than or equal to a value, or whatever. These are the only two data points that we need. But for a multivariate normal distribution with 2 stocks, we're going to need two means and 2 variances, 1 for each of the variables. But then to connect the 2, we would also need the correlation of the 2 variables, or else, if we just had the mean and the variance, we're just modeling them independently. But we need to know how the relationship models to each other, and we do that through the correlation. So here we have 2, 4, 5 parameters that we need. Our answer is C. Before we continue with the questions, I just wanted to show you something really quickly in Excel, which is related to the idea of standardizing a normal distribution. So the whole idea around standardizing a normal distribution is that you can take a variable that has a mean and standard deviation that are different than the standard normal distribution, where the standard normal distribution has a mean of 0 and a standard deviation of 1, which is this graph right here. So the mean is 0 and the standard deviation is 1, and everything goes, all the results float in a normal distribution around 0. In the case that you have a distribution that is normally distributed, but is distributed around a mean that is different than 0 and a standard deviation that is different than 1, you might have something like this. So I have a mean of 1 and a standard deviation of 2 here, and you can see that in the green chart, it is distributed around the value 1, and it still follows a normal distribution, but it's not the standardized normal distribution, which is around 0 and 1. And the whole idea around standardizing is that if you have two different data sets that are normally distributed, but you might have a mean of 1 or a standard deviation of 2, or like a mean of 5 and standard deviation of 7, whatever, you want to be able to compare those two data sets. So in order to do so, you use the z-score of those values to essentially convert these values here into a standardized value from then which you can compare the multiple data sets. So there's something I wanted to touch on really quickly. I thought the graph would help clear it up. So with that, let's get back to the questions. An analyst develops the following capital markets projections. We have stocks and bonds, and we have a mean return and standard deviation of each. Assuming the returns of the asset classes are described by normal distributions, which of the following statements is correct? So let's eliminate some easy ones first. So B, on average, 99% of stock returns will fall within 2 standard deviations. It's incorrect. That's 3. If it was 2 standard deviations, it would be 95% of returns would fall within 2 standard deviations here. So this one's incorrect. C, the probability of a bond return less than or equal to 3% is determined using a z-score of 0.25. So here's where standardizing the returns comes into play. So bonds, kind of like what I just showed you in Excel, we have a distribution that's normally distributed, but the mean and standard deviation are different than the standard normal distribution, where the mean is 0 and the standard deviation is 1. So here we're going to standardize this. And the probability of a bond return being less than or equal to 3%, we got to calculate the z-score. So we have 3% less 2% divided by the standard deviation, which is 5%. And we end up getting 1 over 5, which is 0.2, or 1% over 5%, which is 0.2. So that is not equal to 0.25. C is incorrect. A is going to be right, but we can go ahead and show why. Bonds have a higher probability of a negative return than stocks. So having a negative return means that the z value is 0, or not the z value, but the value that we're using here. So the value of the stocks or the bonds. So for stocks, it would be the z-score is 0 minus the mean, which is 10 over 15. So that is 0.67, negative 0.67. And then for bonds, we have 0 minus 2, which is the mean, over 5. So we have negative 0.4. So if you bring these, now we just standardize these. So if you look at the z-score of bonds being less than 0 is negative 0.4, so it would be like right here. And for stocks, it's negative 0.67, which is somewhere around here. So there's more probability contained to the left of the z-score for bonds. So 0.4, you can see it has all this extra space, and there's more probability contained there than the probability to the left of the z-score for the stocks. So client holding a 2 million pound portfolio wants to withdraw 90 grand in 1 year without invading the principal. According to Roy's safety first criterion, which of the following allocations is optimal? So we have allocation A, B, C. We have an expected annual return for all 3 and standard deviation of returns for all 3. So the safety first criteria, the formula for it is the expected value of the return on the portfolio minus, you can put X, but this is basically our target return, and divide that by the standard deviation of returns on the portfolio. And what this ratio tells you is the probability of having a return at least as equal, or at least as big as this. So if we're looking at the question, we have 2 million and we want to withdraw 90,000. So we need a return of something such that when we withdraw it is not less than 2 million. So the return is actually, the return that we need is 90,000 over 2 million, which is 4.5%. So we can sub that in as our target return here, and then calculate this safety first criteria or the probability of exceeding this 4.5 using the inputs for all the different portfolios. So we have A is going to be expected return of 6.5 divide or subtract 4.5 over 8.35. We're just going to put all the inputs for all of them first. B, the expected return of 7.5 minus 4.5 is our target over 10.21. C, 8.5 expected return minus 4.5 target divided by 14.34. And if we run all these out, for A we get 0.24, B we get 0.294, and for C we get 0.279. So if we're looking at them, B has the highest ratio or the highest probability of at least getting a 4.5% return. So B is our answer. A is going to be our answer. The weekly closing prices of Mordees Corporation shares are as follows. August 1st, 112, 8th, 160, August 15th, 120. The continuously compounded return of the shares for the period from August 1st to August 15th is closest to what? So we have August 15th, 120, and then August 1st, 112. So this kind of goes back to what we were talking about in the time value of money with the frequency of compounding and how there's different return calculations for that. So remember that for continuously compounded returns, we got to use Euler's number in the calc. So if you were to try to solve for R, where we have a starting value of 112 and a closing value of 120, it would look something like this. So 112 times Euler's number to the R. So this is how you compound the initial present value with a continuous return. So times Euler's number to the power of R, and the R is what we're solving for, equals 120. So now we can use some algebra and isolate for R. So we can have Euler's number R equals 120 over 112. And now to get rid of this Euler's number, what you do is actually take the natural log of both sides of the equation. So if we do ln ER equals ln 120 over 112, and then this and this cross out, and the R comes down. It's not the exponent anymore, so R is ln 120 over 112, and we get an answer of 6.90%, which is A. Just got to remember for continuously compound returns, always use Euler's number, and to get rid of this, it's the ln of both sides. In contrast to normal distributions, log normal distributions are skewed to the left, have outcomes that cannot be negative, are more suitable for describing asset returns and asset prices. So here I've drawn the standard normal distribution. So we have a mean of 0, standard deviation of 1. If you wanted to take or get a log normal distribution, all you would do is take Euler's number of x, where x is the normally distributed variable. And what you would end up with is a distribution that looks like this in the light blue. So this distribution is, it can't be less than 0. E to whatever can't be less than 0. And then it's also skewed to the right. I know the graph kind of looks like it's skewed to the left, but it's intuitively, it's kind of the opposite. That's how I think of it anyway. And if we take this information and go back to our question, log normal distributions are skewed to the left. Nope, they're skewed to the right. Have outcomes that cannot be negative. That is true because they're bound by 0. And C are more suitable for describing asset returns and asset prices. That's actually this next question right here, which we can eliminate this and answer this at the same time. 31, The log normal distribution is a more accurate model for the distribution of stock prices than the normal distribution because stock prices are symmetrical, definitely not. They're, can be all over the place. Unbounded. So unbounded means if something's bounded, it's bounded either at the negative values or at the positive values, to the left or to the right. So stocks cannot be less than zero. So they are bounded by zero. They can obviously go to infinity on the positive side, but they're bounded by zero. And that goes into C, where the log normal distribution is better for modeling stock prices because stock prices are non-negative. So this is correct. This is incorrect. Here we're getting into the first time that we're talking about a distribution other than the Z distribution, where we're talking about the student's T distribution. And just to back up really quickly, a distribution, all it is a range of possible values that a variable can take. So the Z distribution is what we've been talking about. Here we're discussing the differences between the Z distribution and the T distribution. So I have a chart down here from the internet, which we'll get to in a second. But look, going back to the question, which one of the following statements about student T distribution is false? It is symmetrically distributed around its mean value like the normal distribution. If we come to the chart, you can see the T distribution is in red and green. We'll get back to the differences between the two in a second, but across both, the distribution is symmetrical around its mean. So this is incorrect. Well, it's correct, but we're looking for what's false, so this is not the answer. For B, it has shorter, aka thinner tails than the normal distribution. So if we're looking at, we can just take the red one as an example. So the red T distribution, it actually has longer and fatter tails than the normal distribution. And all that this really means is that the T distribution is going to provide more conservative estimates. And what it means by that is that, for example, the probability that the distribution takes a value less than whatever this is here, I just drew a line like negative 0.5, is greater in the T distribution than in the Z distribution. There's more probability underneath this curve here. So there's going to be more probability that the value is going to be less than this, which leads to fatter tails and a more conservative estimate. So this is actually incorrect, and we're looking for what's false. So B is the answer. Got to be careful with, when they're asking you to find something that's true or false. And then for C, we know this isn't the answer, but we can look at it. As its degrees of freedom increase, students' T distribution approaches the normal distribution. So the main difference between the T distribution and the normal distribution is that for the T, we assume that we don't know the actual variance of the population. And due to that, the T distribution is typically used when we have data with less than 30 samples. And as the degrees of freedom or the sample size, they're pretty much the same thing. As the sample size increases, you can see that it approaches the normal distribution. So if we have a T distribution with n close to 30, you see that the red line starts to mirror the blue line, which is a normal distribution, a little bit better, versus if we have a T distribution with less than 30, maybe like 10 sample values, it's going to be scrunched up a little bit more and not really reflect the normal distribution. So as degrees of freedom increase, aka sample size, it's pretty much a sample size, not exactly. The degrees of freedom is actually the sample size minus 1, but that's just small technicality. But anyway, as the degrees of freedom increase, it starts to approach the normal distribution more. So this is true, and it is not false. So that's not our answer. Also, one more quick note on this one. In the curriculum, it says the correct answer is A, but then it describes B as being the correct answer. So it's just a typo in the curriculum. The correct answer is B. Here we're talking about chi-square and F distributions. So this is the first time we've talked about distributions other than the normal and T distribution. For the exam, the normal and T distributions, in my opinion, are most likely to be tested. Here with the chi-square and f, I'm going to go into some detail and describe them. It's probably a little bit more detail than you actually need, but just in case you were curious, I wanted to clear some things up. So really quickly, the chi-square distribution, once again, this is just a way to model potential values. This distribution takes the sum of squares of a normally distributed variable, so x squared, and it models that, whereas the f distribution takes the ratio of variances of two normally distributed independent variables, so it's the ratio of like variance x over variance y, and the distribution looks something like this. On the exam, not too important to know exactly how these are calculated. The most important thing, which is something we're going to touch on a later module, is when to use the f distribution, chi-square distribution, z distribution, and t distribution in a hypothesis test. So which one is applicable for when you're testing different hypotheses. And once again, we'll get into that a little bit later. But for now, let's get back to the question. So we're looking for what's false. A, they are both asymmetric distributions, which means not symmetric. So you can kind of see these are both not symmetric. That's not the answer. For B, as their degrees of freedom increase, the shapes of their probability density functions become more bell curve-like. So if we come to chi-square, the degrees of freedom is over here. It's the same concept as the t distribution here, just they're labeled differently as k. So you can see with the degrees of freedom of 1, we have this blue graph. And then as we increase to 10 in the green graph, it does become more bell curve-like. So that's true. And it's the same case for the f distribution. Here, once again, the degrees of freedom are labeled a bit differently. And we have 2 degrees of freedom because we're dealing with 2 parameters. But same kind of concept. If you come to the green one where both degrees of freedom are 10, which is greater than everything else, you can see the green distribution becomes more bell curve-like. So this is true and is not the correct answer. Finally, C, this is going to be our answer, but we'll talk about it anyway. The domains of their probability density functions are positive and negative numbers. They're not negative, they are only positive. They're bound by 0 in both cases. So this is false. Really quickly, before we go to the next questions, I just want to hop back into Excel quick. The next couple of questions are talking about Monte Carlo simulations, so I just wanted to demystify them really quickly. For someone who's never seen it before, it might be completely foreign to them. I just want to show you how easy it is to create one in Excel. The whole idea around a Monte Carlo simulation is just running a bunch of outcomes for random variables. So in this example here, I could pretend I'm rolling 2 dice, dice 1, dice 2, and each dice can take a random value. So I'm using the ran between function. So a random value between 1 and 6, same one for dice 2. And then down here, I'm taking the sum of both. And what I'm going to do is I'm going to simulate this 100 times and see what the results are. So this cell here, I'm actually just taking the sum of the dice above. And if I highlight this whole table and I go into data and what if, go to data table, the row input cell can be blank. Don't have to get into why. Column input cell can be anything because we're just doing random variables. Click OK, and you can see that all these values populate. And if I was to reset or just trigger a new calculation, all these values are going to change. So this is basic. This is the basics of a Monte Carlo simulation, just running a certain random event a bunch of times, and then you can do some analysis. Like here, I could calculate the probability that the sum of the dice rolls is less than 4. So I could take, count if this range is less than 4 and divide it by the total number of outcomes, which is 100. In this case, it's 10%. I could reset. Now it's 5%, reset 12%. In practice, these simulations are usually ran, I believe, 10,000 times. I just did it 100 for this time, but the concept's still the same. So with that, let's go back into the questions. These next 2 questions are both about Monte Carlo simulations, so we can do them both at the same time. Monte Carlo simulation can be used to directly provide precise valuations of call options. Options we'll get into a little bit later in derivatives. There is some simulation involved in calculating the value of them, but the keyword here being precise, it's a simulation, so it's not precise, so it's not right. Can be used to simulate a process from historical records of returns. Historical is more related to back testing. this is when you would like take, for example, like a historical record of returns and then back test a trading strategy using 5 years of data to see if it would have been profitable in the past. So this not really relevant. And then C, test the sensitivity of a model to changes in assumptions, for example, on the distribution of key variables. So you can see from the Excel that we just went over, that could easily be used to flex certain variables in a model, whether it's like revenue growth rates, COGS, percentage of revenue, stuff like that. You could flex the sensitivity of that by running simulations. So C is our correct answer. Next, a limitation of Monte Carlo simulation is its failure to do what if analysis. I mean, we just saw in Excel, it's literally under the what if tab. So it is a what if analysis, like we're calculating a range of outcomes if the variables took different values. So this is not true. B, it requires historical record of returns. That's not true either. We could use whatever assumptions that we want in a simulation and forecast that forward. And then C is its inability to independently specify cause and effect relationships. This is going to be the answer. Basically, the Monte Carlo simulation is just flexing a couple variables. It doesn't really incorporate the interdependence of them. Like you could model, like run a simulation for stock price returns, accounting for their correlation, but that's just more of it's just identifying the relationship or the correlation between the two. It doesn't really identify cause and effect, what's causing what. So this is going to be the answer. A little bit of a tricky one, but just something to note. You can check the notes for more of the advantages and limitations and disadvantages of Monte Carlo simulation. It's good to at least skim them over so they're not completely foreign if they show up on the exam.